Okay, good. Right, so welcome to Euclidean geometry. And I know, again, for the rest of you guys, I know how much you guys love Euclidean geometry. Okay, every single year, it's quite funny. It happens in grade 11. So every single year in grade 11, somebody goes and as a group, they decide they hate a particular section. Last year's grade 12, it was trigonometry. They hated trigonometry. The moment I even uttered the words trigonometry, you could literally see the panic attacks happening, like a basically wave of panic attacks. Okay. Now, you guys, luckily, the trigonometry is not your issue. You're actually kind of okay with trigonometry, which I'm very happy about, because otherwise I might have started developing some PTSD. But you guys, last year, I saw how you reacted to the Euclidean geometry. That was literally your waves of little panic attacks, like the Mexican wave panic attacks going through. So we need to get a handle on the Euclidean geometry. It is a very, very important section. And the issue comes that a lot of times you go and say, oh, but that's grade 11 stuff, maybe the grade 12 stuff will be better. Now initially, when we start the grade 12 Euclidean geometry, you'll see that it doesn't really have that much to do with grade 11. Until we get to the second section. There are two sections. The first section we're going to be doing this week, which is called the proportional division theorem. That doesn't really have anything to do with the grade 11 Euclidean geometry. But the moment we get to the second section, which is called similarity, then you're going to need all of that information from the grade 11 circle geometry. Okay, and I think you guys also saw in analytical geometry how important it was to remember some of your Euclidean geometry theorems. I did summarize it very nicely for you guys. I did go and say, you need to understand that the tangent is perpendicular to the radius. You need to understand that tangents from the same points are equal. I did show you all of that specifically for the analytical geometry, but it's going to become important again when we get to the second section, which is similarity. Okay, so let's talk about the proportional division theorem. We first need a couple of background information pieces. And the first one, silly little thing, area of triangles. Okay, how do we calculate the area of a triangle? Anyone? Half base times perpendicular height. Simple, straightforward, easy. Half base times perpendicular height. However, where the base and where the height is located, that sometimes is a bit of a tricky problem. The base must always be one of the three sides of the triangle. You cannot have a base that is not one of the three sides. Are you all aware of that? Good. The height must always be perpendicular to the base. Always. So, if you say this is the base of the triangle, the height must be perpendicular at a 90-degree angle to that base. If you say this is the base, then the height can actually be one of the three sides of the triangle because it must be perpendicular to the base. And over here, whoops, what's going to happen over here? How am I going to get a height perpendicular to the base? Oliver?
The height is going to be the distance from the base to the end
Yes.
point.
The height can actually be exterior to the triangle. Okay. So if you have an obtuse angle triangle like that one, it is quite possible that I will have to put the height outside the triangle, which means I need to extend there to get that 90-degree angle so that this is the height. So please remember, it is completely possible to have a height that lies exterior to the triangle in order to get that 90-degree angle in there. That's something a lot of people forget because we don't do it a lot. Okay. Then, like I said, the area of a triangle is going to be half times the base times the perpendicular height. And you'll see just now why this is important to remember. Now, another thing that I'm not exactly sure if you are aware of this. If I take these two triangles, so I've got a black triangle, and I don't know if you see, I did try and highlight the red one. So you've got the black triangle, triangle ABC, and you've got the red triangle, triangle ABD. Can you see that? Now, what can you tell me about the heights of those two triangles? They're the same. They're equal. They have the same height. Because if I drop a line down here at 90 degrees, then that line comes from vertex A, down 90 degrees to both of the bases. They have different bases. That I can completely confirm. The first triangle, triangle ABC, has a base of BC. That's the base. Whereas the red triangle, triangle ABD, has a base of BD. So careful. They don't have the same areas. You can notice they don't have the same areas, but they do have the same height. Everybody agrees with that? Okay, so let's write this down. The area of triangle ABC is then half, which is the base, which is BC, times the perpendicular height, and I'll put the height over there. And the area of triangle ABD is half times BD times that perpendicular height. And the deduction we have to make there, the very important deduction is this. If two triangles share a vertex, okay, you guys know what a vertex is. That's the pointy bit. Okay. So if two triangles share a vertex, they can have a common height. Two triangles that share a vertex have a common height. And like I said, in this case, it's A. They have a common height. And again, you'll see just now why this is important. All of this is background information, because I'm going to discuss the theorem with you just later on, and then after we've done some practice with the theorem, I'm going to be doing the proof of the theorem, and it's in the proof of the theorem that you need this information. Otherwise, the proof of the theorem is just going to go. Okay, right, next. Now, this is quite interesting. If I take two parallel lines, by the way, if you're a little bit behind on the notes, please don't stress. Like always, I will scan them and I'll upload them to the Google Classroom. Always, always, always. I'm not going to stop doing that anytime soon. Okay. So if I take two parallel lines and then I go and I draw two different triangles on those parallel lines. So let's say the first one goes over here. So there's my first triangle. And I'm going to draw a second triangle. And then I'm going to name these two triangles. I'll say this is triangle A, B, C, and then I'll do that's D. Got it? Now, what can you tell me about those two triangles from the discussion we just had about area of triangles? Yes. They've got the same height, absolutely, because of the parallel lines. So because those two triangles are stuck between these parallel lines, this one, the height's going to be over there. This one, the height's going to be over there. But because of the parallel lines, the distance between them are the same, so the heights are the same. Do you guys agree? What else can you tell me about these two triangles? Yes. Same base. Those two triangles, because of parallel lines, have the same base, they have the same height, therefore they have the same area. So I can go, and by the way, this is a Euclidean geometry theorem that we've never actually taught you, but you can totally and utterly use. It's the Euclidean geometry theorem that says triangle ABC, the area of triangle ABC, I should rather say, is equal to the area of triangle BCD. And the reason is same height and base. And you can use this in Euclidean geometry. You can totally use this in Euclidean geometry. Logically speaking, two triangles that share a base, so they've got a common base of BC, and because their vertices go to those parallel lines, they've got the same height. So same height, same base, means same area. And we're going to be using this again later on when we prove the theorem. But it's quite a nice one to know. Okay. be aware of this one. Now, the next thing we have to quickly talk about, we have to talk about ratios. And this, I find, is the trickiest thing we have to discuss, because when was the last time you guys did ratios? Can you remember? Grade 9-ish. Like, really? Yeah. Pretty much the very first chapter we did in grade 9 mathematics with you guys was a discussion on ratios. Remember, like for instance where they said you have a bag of 24 cookies and you want to share it in the ratio of 1 to 3 between you and your older brother. Do you guys vaguely remember that from grade 9? Vague, I know, vaguely. And then also, we did do something in grade 9, which again you might have completely forgotten. We did congruency of triangles, but we also did similarity of triangles. And we said when we do similarity of triangles, we said that the sides have the same ratio. So we did use the words ratios, but unfortunately we haven't done it for a while. That's why Mr. Kenyon was actually quite funny when he made the joke yesterday, where he said, yeah, you guys won't understand the math lit content. And to a certain extent, there are certain advantages that the math lit people have, because they've been doing ratios and percentages for the last 3 years. You know, all the stuff that you did up until grade 9, they've been doing it again and again and again. So those of you who do 8-subject math lit, you might actually find that this section is not too bad, well, aside from the Euclidean geometry, but you will understand the ratios better than the core maths people, because the core maths people haven't really done ratios in about 2.5 years. You understand? So let's just do a quick recap on ratios. The quick recap says, most of you guys are perfectly capable of dividing things into equal bits. Like if I tell you, here you go, divide that half-half between you and your brother. You'll go like, oh yeah, look, there's half, there's half. Most of you guys get that half-half. Some of you guys, like me for instance, I'm one of 5 kids. I was raised with 4 siblings. I know, shock, horror. Don't know what my parents were thinking. But anyway, especially since I'm the second eldest, they should have just stopped after 2, you know? Okay, anyway, so I am very good at dividing stuff into 5. You give me anything in the world, and I can divide it into 5 perfect slices, or 5 perfect bits. Most people are fine with that as well. They can divide it into 5, but the idea is that each piece is equal. The problem with a ratio is, a ratio now says, we are going to be dividing it, but we're going to be dividing it, like for instance that one, in the ratio of 4 to 3. And you go, what? Okay. So let's quickly talk about that ratio of 4 to 3, because a lot of people seem to misunderstand that you are still dividing it into equal bits. But you are dividing it into how many equal bits? Can somebody tell me? 7. You are dividing it into 7 equal bits. That's what you're going to do. Got it? So the idea here is this. We're saying that AC over CB is equal to 4 over 3. And whenever you write that down, that ratio that you're dividing it into, I want you to have the habit, very important in this section, immediately do this. Now let me explain to you why I immediately put a variable, don't use x ever. Use something like a k or an l or an m, the latter part of the alphabet. You can use a p or a q, that's absolutely fine. But the reason we're doing this is the following. A lot of people seem to misunderstand the idea of a ratio. They think the ratio tells you exactly how big the length of the side is. So a lot of people think that if I say AC over CB is 4 over 3, they seem to think it means AC is equal to 4 units or 4 centimeters. And they seem to think that CB is equal to 3 units or 3 centimeters. No. The ratio was simplified, meaning, sure, it could be 4 over 3. It could also be 8 over 6. What is 8 over 6 simplified to? 4 over 3. It could also be 16 over 12. What is 16 over 12 simplified to? 4 over 3. So the problem with a ratio is the simplest version of those lengths of 2 sides. So you can't just simply go and say the one is 4, the one is 3, because if you make the assumption this is 4 and this is 3, it's clearly wrong because I told you the entire length is 21. So it's impossible for it to be 4 and 3 because 4 and 3 is not 21. 4 and 3 is 7. Do you understand? So what this is actually telling you is it's telling you the following. AC is 4 bits. And each one of these bits is like 1K. So that all together makes up 4K. Do you understand? And that K is pretty much the whole idea behind it. It could be, it's a constant multiple. Do you understand? It's a constant multiple. So it could be 1, which means it's 1 plus 1 plus 1 plus 1, which means it's 4. It could be 2, that constant multiple, K could be equal to 2. And if K is equal to 2, it could be 2 plus 2 plus 2 plus 2, which means it's equal to 8. It could potentially be 3, which means it's 3 plus 3 plus 3 plus 3, which means it's equal to 12. K is a constant multiple. Okay, and then in exactly the same way, this thing is also 1K, 1K, and 1K, so that this is then equal to 3K. Now, the moment I do it like that, then you guys can hopefully see how to work out the value of K. Can you see how to work out the value of K? How would you go about doing that? Yes?
Get the coefficient of K to 1.
Yes. Pretty much what we're saying is we're saying there are 7 bits here. Do you understand? So to get that bit, the K, which is the bit I'm talking about, we are going to say that 4 of those plus 3 of those add up to 21. Do you guys agree? 4 of those bits plus 3 of those bits add up to 21, which is why we said we divided it into 7. So what is my K value then? 3, which means that AC is 4 of those bits of 3. So it's 4 times 3, which means it's 12. And CB is 3 of those bits of 3, which means it's 3 times 3, so it's 9. And that makes sense, because what is 12 plus 9? 21. So watch out for these ratios, please, guys. The ratios, a lot of people just make an assumption saying, oh, that's equal to 4, that's equal to 3. No, it's equal to 4 bits. That's why you use the K or the P or the L or the N. You'll see later on when we do these examples what I mean. You have to keep on using it. Okay. And that's how you can work out what the value of that multiple is, what the value of that K is, and then you can translate that and see what the actual length of the sides are. Okay, right, next. Cross multiplication. You're going to go like, what? Is this important? Yeah. How many of you guys know about cross multiplication? Do you even know what cross multiplication is? Yeah. Well, you multiply, over here, you multiply the numerator across with the denominator, and over here you multiply the numerator across with the denominator. You are aware you're allowed to do this. I think you guys got taught this in grade 8 or 9, correct? Grade 10. Okay. So at least you are aware of the fact that you can do this. You are allowed to go and say A times D is equal to B times C. Now, again, this is stuff we're going to be using, and so I'm just checking to make sure you understand. But I can go, and I can do even more with this. I can go, for instance, and now that I've got that one, I can say, you know what? I'm going to go and I'm going to divide both of these sides by A. So if I divide this side by A, I'm going to get D over AD divided by A is D, and BC divided by A is BC over A. So I can get that. You understand? I can play with this. I can even do the following. I can say B over A is equal to D over C. Why am I allowed to do that? What did I do? Flipped it, reciprocal. Do you understand? I wrote the reciprocal on the left-hand side, I flipped it, I interchanged the numerator and the denominator, and I flipped it on the other side. And then I can again go and I can multiply across, which means A times D to B times C. There's a lot of stuff I can do here. Do you understand? And you'll see in the notes, they've actually gone on page, where's this? On page 3, and they've shown you all of the different variations that you can get. So on page 3, they've shown you all of the different variations you can get with this cross multiplication. Okay, so you can take a look at it, you can play with the cross multiplication, but later on, when we start doing the examples, you'll again see what I mean with having that cross multiplication, doing the reciprocal, rewriting it. It all has to do later on with ratios. Okay, so this is the background information. I'm just going to stop this video so can I record another video to now get into the theorem.